So let's look at some examples worked out. These are the examples that are in your notes of collecting a gas by water displacement. Now, I've already underlined the important information and said the gas was collected over water. This is how you will know it's a Dalton's Law problem. So where you're going to have to subtract off the water vapor. Remember, the barometric pressure is the total pressure. They're also going to call it maybe atmospheric pressure. They want us to find the partial pressure of oxygen. That's the pressure of the gas we're collecting. And they say it's at 20 degrees Celsius. So that means in order for us to get our vapor pressure of water, we're going to have to look on our vapor pressure chart at 20 degrees Celsius. So if you look, that's 17.5, and that's in torr. So that's where I got 17.5 torr. So now we're going to plug into the rearranged formula for Dalton's Law. The 25 torr is your total pressure or barometric pressure. Subtract your 17.5 torr from it. Remember, you go at least decimal places when you subtract. So we're going to round this to the whole number. So we got a total of 8 torr. This is the partial pressure of oxygen gas that was collected. Now, typically, when you get this pressure of your gas, once you get the individual gas's pressure, you would then want to maybe plug it into the ideal gas law or maybe another gas law that has pressure in it and solve. So you'll be using this gas law here in conjunction with our other gas laws that we've been learning about. All right, let's take a look at example 2. Your second example says helium gas is collected over water. If the atmospheric pressure, remember that's something else they're going to call the total pressure. If the atmospheric pressure is 0.962 atmospheres at 35.5 degrees Celsius, 35 degrees Celsius, what's the partial pressure of helium? So again, we're going to have to go to our vapor pressure chart, find 35 degrees Celsius, and that's where we're going to get our corresponding water vapor pressure. Here's 35 degrees Celsius. So it's going to be 42.2, and that's in torr. So you want to be careful with that because remember, this total pressure is given in atmospheres. So what I did first is I said 42.2, and I converted it to atmospheres. Remember, we learned that 760 torr is equal to 1 atmosphere. This has 3 significant figures. So we're going to round this answer so that it has 3 significant figures. Recall that leading zeros do not count, so this is your number written to 3 sig figs. So now we have our pressure of our water, vapor pressure in atmospheres, and the total pressure was in atmospheres. So we can plug it into our gas law. 0.962 minus 0.0555 atmospheres, and we're going to round to least decimal places. This has 3 decimal places, this has 4 decimal places. So we're going to round our answer to only 3 decimal places. 0.906 atmospheres is your answer. Again, normally when you get the pressure of your gas, you're going to then plug that into another gas law. And we're going to do one like that next. Our final example, example 3 in your notes, you will notice immediately that it has way more information in it. Okay. So this says oxygen gas is collected over water at 25 degrees Celsius. And then it goes on to say the volume of oxygen collected was 750 milliliters at a barometric pressure of 755 millimeters of mercury. That's your P total because they call it barometric pressure. And it says how many moles of oxygen were collected. Now remember, y'all, when you see moles, that lets you know it's an ideal gas law problem. So not only are we going to have to use the pressure of oxygen is equal to the total pressure minus the pressure of water, we're also going to have to use the ideal gas law, PV-nRT. So first thing I would do is I would go ahead and subtract off the water vapor like the last 2 examples we did. So 755 millimeters of mercury minus 23.8 torr. Now, I do want to remind you, the chart is giving you your pressures in torr, but a torr and a millimeter of mercury are equivalent, so you can just substitute here and you can go ahead and subtract. You get 731 millimeters of mercury. Now recall, for ideal gas law, we cannot leave our pressures in millimeters of mercury because we're using the R that has atmospheres in it. So this number now plugs in as a given into the ideal gas law. So I went ahead and did my conversion here and converted it to atmospheres. Now the volume was given 750 milliliters. Now remember, for ideal gas law, we have to have our volume in liters for the R that we're using. Moles is what you're looking for. R is 0.08206 liter atmosphere per Kelvin mole, and the temperature is 298 Kelvin. You remember, you always plug in your temperatures in Kelvin into any gas law. So now we have everything in the proper unit and we can solve for N, moles. So I wrote down my rearranged formula to isolate my variable. We're going to plug into the formula 0.962 times 0.75 divided by 0.08206 and divided by 298. Now, if you look at your numbers here, your sig figs you need to round your answer to two significant figures. So I wrote my final answer, 0.030 moles of oxygen. Now, you could also, once you subtract here and get your partial pressure of your gas you collected, sometimes you might plug into a different gas law. It's not going to always be the ideal gas law. This problem, it was because we wanted moles. But it could be that you're plugging into the combined gas law or Boyle's law or even Gay-Lussac's law. All right, so these are our examples. We'll do some more of these on the homework and practice them in class some more as well.